Hey everyone. So in this video, we're going to just wrap up part of the lesson 3 from today, or from this week. So I'm going to open up my slideshow, and we are going to go through it. So we're either watching this video because we didn't necessarily finish everything in class this week, or unfortunately, you have the class on Friday, so you're missing a lesson, and it's just kind of like a way to catch up and get an understanding of what the follow-up assignment is going to entail. So at this point, we've done some balancing equations. We did some practice with it. Now, we know what to do to balance an equation. But why are we spending time learning how to balance chemical reaction equations? What is the purpose behind this? So we know that in terms of actual physical materials, in terms of mass, that the law of conservation of mass states that each side of a reaction must have the same exact mass. So that means that the same number of atoms of each element are present on both the left and the right side of the arrow, so the reactants and the products. But why is this important to us? So we can think well, yes, we can't create or destroy mass. We can't change the amount of something we put in to get something that we put out. But why does this relate to us? So take some time and think about why we need to know how to do it. Okay. So how you kind of fleshed out this thought, let me go over why exactly this is kind of important. Now, you don't need to write this down, but it's just something to keep in mind as we go forward. So we're going to focus on specifically the products of a chemical reaction. So the number of moles of a product of a reaction is going to be equal to a specific mass of that compound. So we're not just writing out these chemical reaction equations for fun. There are purposes to each and every single type of chemical reaction. We're trying to create something. We're trying to make something, synthesize something, or break down something into something else. But we're going to kind of focus on the making of things, so the synthesizing. So if we want to determine how much of a specific compound we want to make, we need to know how much reactants are needed without wasting materials. So you can kind of think of this as baking or cooking in general. So if I'm trying to bake a cake and I know that I need a certain amount of flour, sugar, butter, eggs, etc., and that recipe is going to yield whatever cake I need. So if I'm making just a regular cake for a birthday or a dozen cupcakes, I know how much of each ingredient I need. But if I stray from that, if I change the amount of eggs, flour, butter, sugar, etc., then that's going to, one, potentially make the reaction not go well, so not make a good cake, or make too big of a cake or too many cupcakes or something. And we want to make sure that we're making the right amount and the right product. So I want you guys to kind of think about that as we go forward with this. But we are going to look at a specific chemical reaction, an example of this. So say I wanted to make my own batch of table salt. So stuff at the store, not good enough. I'm going to make my own. So there is a balanced chemical reaction in order to make this. So table salt is sodium chloride, NaCl, S stands for solid. And in order to create it, I need sodium, pure metal, and then chlorine gas, that's Cl2. If I take this unbalanced reaction and then balance it, I get 2 moles of Na, sodium, plus 1 mole of Cl2, I'm just going to put a 1 here, yields 2 moles of NaCl solid. So 2 moles of sodium plus 1 mole of chlorine gas will give me 2 moles of sodium chloride, my table salt. So once again, if I want 2 moles of this, I'm going to need 2 moles of Na and 1 mole of Cl2. But we don't necessarily think in terms of moles or molecules. We think in terms of mass, or that's how we measure things. I can't go and get a scale and read, hey, I need 1 mole of sodium. I need to know a specific mass of it. So think back and try to remember, how do we determine how much of each of these ingredients we will need? Specifically in terms of mass, how do I know? So hopefully you think about the idea of the molar mass. So once again, if I want 2 moles of sodium chloride, I'm going to write here. So if I want 2 moles of NaCl, I know I need 2 moles of Na and 1 mole Cl2. And in terms of mass, I need to look at the molar mass. Well, for sodium, the atomic mass, but I need to know essentially how much of the specific compound I need in terms of actual grams. So we're going to keep this in mind. So to create this number of moles, I need 2 moles of sodium, 1 mole of chlorine. And I need to look at this through the lens of the molar mass. Okay. So I'm going to jump forward a little bit. I'm going to clear this. But what if I just wanted 1 mole of NaCl? So like this reaction, when it's fully balanced, tells me how to create 2. But if I only want 1 mole, how do I determine this? So we can kind of look at the proportions or the ratios involved here, and that's what we're going to be focusing on. So I know that if I want to create 2 moles of NaCl, I need 2 moles of Na and 1 mole of chlorine, Cl2. But if I want to create just 1 mole of NaCl, I'm really just looking to split this recipe in half. So like, if you see a recipe and it says 4 servings, but you only need to serve 2 people, why are you going to make all 4 servings unless you like leftovers? So we're going to just cut this recipe in half. So to make 1 mole of NaCl, I need 1 mole of Na and 0.5, half a mole of Cl2. Now, to determine the mass involved here, we're going to look at this molar mass. So just for an example, if I look at the molar mass of sodium, or really, like I said, the atomic mass, it's going to be about 23 grams. That's 1 mole. If I look at Cl2, it's about 70 grams per mole. There's 2 of them. But if I only need half a mole, we know how to do these molar conversions. We're going to be using this idea. So take another look. We have our table T, and we have that molar calculation formula, where it was number of moles equals given mass over gram formula mass, or the molar mass. So if I know I need 0.5 moles, I can put that into here. And solve for my given mass, because I have my molar mass of 70 grams per mole. So this would tell me how much chlorine I need to physically create 1 mole of sodium chloride. Sodium chloride. So this is where we're going to be going into. So this is going to be our next step here. Okay. Now we're going to take one more look at this in a different lens. So here, previously, we kind of looked at if I needed 2 moles of NaCl, what do I do? Here I'm looking at if I need just 1 mole, what do I do? So I'm going to clear this and jump to the next one. So now if I wanted 1 cup of NaCl, so a cup, when you actually measure out the mass of it, is equal to 273 grams. So I need 273 grams of NaCl. How would I go about determining what I need here? How much sodium, how much chlorine? So once again, we're going to kind of think back to our molar conversions. And we're going to take a look at the molar mass of sodium chloride here, because we have the grams So we know how much salt we have, we want. NaCl, if I look up the molar mass, it's going to come out to about 58 grams. Oops, sorry. So 1 mole is equal to 58 grams. But I want 273 grams. So we can look at our molar conversions again. So once again, our molar conversions, or our mole calculations, I believe is how it's labeled on table T. We have number of moles equals the given mass, ugly G, sorry, given mass over the gram formula mass, or the molar mass. I like writing molar mass. Now I could apply this to this situation. If I'm given 273 grams of NaCl, and I know the molar mass is 58, I can determine how many moles of sodium chloride I need to create with this. So 273 grams divided by 58 grams per mole, and that's going to give me, sorry, I'm just going to calculate this real time. About 4.7 moles of NaCl. So this is telling me that if I want to create 1 cup of NaCl, I need that for a recipe, 273 grams worth. I need to come up with a reaction to produce 4.7 moles of sodium chloride. That's because 1 mole is equal to 58 grams. I have 273 grams altogether. So my number of moles equals 273 over 58. How do we determine how much sodium and how much chlorine we need? That we're going to look at in our follow-up activity. So take a thought with it, see if you can figure it out. And we are going to kind of like move on with this. Okay. So there are a couple more things that we are going to look at from this lesson before you get into it. So I'm just going to clear this. And we're going to like focus on what this topic is today. So what we're going to be working through is a process known as stoichiometry. So stoichiometry is a quantitative relationship between the reactants and products in a chemical reaction. So by quantitative, I mean numerical. Like quantitative research involves data, numbers. So we're going to be doing some calculations, and they provide us with real physical values of specific compounds. So actual masses and volumes. We're going to be focusing more on the mass aspect of this. Volumes will that's more of like an advanced topic that you would cover in like AP or college chemistry. So what these calculations do, what this process does, is takes chemical reactions with their moles and their mole ratios and converts them into real masses, in grams and stuff. So we're going to do some calculations, and we need to know the following. So we need to know the molar masses of the compound. So if you're stuck on this, check out lesson 1 from this unit, or just check your notes, see how that went. And then we're also going to go over something called a molar ratio. So the molar ratio is just the ratio of the coefficients in the balanced reaction. So we'll go through one more thing with this here. So molar ratio, what this is. So once again, it's the ratio of the coefficients in a reaction. So to determine the molar ratio within a reaction, we need to find these coefficients in the fully balanced reaction. So I have an example of here of the synthesis of water. So taking hydrogen and oxygen and producing pure water, H2O. In this case, it's a gas, but it can be eventually turned into liquid water. So to synthesize water, according to this reaction, we need 2 moles of hydrogen gas, H2, and 1 mole of oxygen gas, O2. And that'll give us 2 moles of H2O, water. So an example of this molar ratio, I can focus on O2 to NH2O. So we need 1 mole of oxygen gas, and that's known by the lack of a coefficient, but we can put a 1 here. 1 mole of oxygen gas to produce the 2 moles of water. So therefore, the molar ratio of O2 to H2O is 1 to 2. So it is simply the coefficients that line up with each one. Another example that we can use from this specific equation is if I look at the ratio between H2 and H2O. So 2 to 2 ratio, which we're going to reduce, simplify to 1 to 1. So what this means is that I need 1 mole of hydrogen gas, H2, to eventually produce 1 mole of water in this specific reaction. So if I have 4 moles of hydrogen gas, I could eventually produce 4 moles of water. If I have 2 moles of oxygen gas, I could produce 4 moles of water because that ratio is 1 to 2. It might be helpful to look at this in the lens of like a proportion. So if I go like H2O to O2 is equal to 2 over 1. So that can kind of like help you visualize this when we do some calculations as well. Okay, then the last one is just a couple of questions that we're going to go over together. Okay, so here's one more example. We have the synthesis of ammonia. So synthesis, once again, we're bringing something together. Ammonia is this compound NH3. And we have this reaction. 3H2 plus N2 yields 2NH3. So we want to know the molar ratio between hydrogen gas, that's H2, and ammonia, NH3. So H2, NH3. I just look at the coefficients here. So the coefficient of hydrogen gas is 3, and the coefficient of ammonia is 2. So the ratio is 3 to 2. There's no way to simplify this. So this is at its like most reduced form. Now, if I had 9 moles of hydrogen gas and an unlimited amount of nitrogen gas, so I have 9 moles of this and as much nitrogen as I need, how many moles of ammonia can I create? So how we would go about solving this is we would set this up in a proportion. So we know that the relationship or the ratio between H2 and NH3 is equal to 2 over, 3 over 2. Now, if I have 9 moles of hydrogen and, like I said, an unlimited amount of nitrogen, so I don't have to worry about that, we want to know how much ammonia I can create. So that's going to be my X. So once again, 3 moles of H2 for every 2 moles of NH3 equals 9 moles of H2, X moles of NH3. I would cross multiply. So 3x is equal to 9 times 2 is 18. Do your math here, and x is equal to 6 moles of NH3. So that is how we would determine the molar ratio. Now, once again, this is something that's going to help tie into our follow-up assignment. So if you need to double check this, you can watch this again, or feel free to reach out to me and ask any questions. All right, so good luck and enjoy your break. Enjoy your week off.